In this and the next few videos, we'll look at diffusion in metals and alloys. We'll start by asking ourselves why we're interested in diffusion. This is because most phase transformation, they are diffusional. Let's look at two examples. The first example is liquid to solid phase transformation. We should be very familiar with this kind of phase diagrams now. At the top, that's liquid, down the bottom, that's solid, and in between, that's liquid plus solid. Assume we have a composition here, and we keep decreasing the temperature. It goes from all liquid to liquid plus solid now. If we read the B content in the liquid phase, it is here. Let's call that BL. Let's further decrease the temperature. And if we read the B content in the liquid phase, it will be here. And let's denote it as BL prime. It is clear that BL prime is greater than BL. What this tells us is as we decrease the temperature, the B atoms are actually diffusing into the liquid phase. Similar observations can be made in solid to solid phase transformation. We will use the iron-carbon system as an example. We know that at high temperature, iron will display the FCC crystal structure, and it is called the austenite. The grain boundary we draw here is an austenite grain boundary. Decreasing the temperature will have a new phase or two new phases form, depends on the exact chemical composition. In this example, let's assume there are two phases. One is called ferrite, which has a BCC crystal structure. The other phase is called cementite. Cementite is carbon-rich, whereas ferrite does not contain much carbon. Therefore, during phase transformation, the carbon atoms in austenite will diffuse into cementite as the cementite plates grow into austenite. After understanding the importance of diffusion in phase transformation, let's look at the types of diffusion. In general, there are two types. You have interstitial diffusion for interstitial solid solution and substitutional diffusion for substitutional solid solution. For interstitial diffusion, since the solid atom is much smaller compared to the host atoms, so these atoms can easily diffuse in the lattice. For substitutional diffusion, since the solid atom is more or less the same size as the host atom, for those solid atoms to diffuse, you must have vacancies in the material. So the diffusion of the substitutional solid solution atoms have to be mediated by vacancies. Due to the much smaller size, the interstitial diffusion is much faster than the substitutional diffusion. I just realized I had a minor mistake here in the illustration. I've got to color one of the atoms to make it a solid solution atom. However, in the case where you didn't have a foreign atom, it is still interesting. The diffusion is called self-diffusion, and self-diffusion is also accommodated by vacancies. Last, I'd like to quickly discuss the highways for diffusion in materials. First, grain boundaries in materials can act as a highway for fast diffusion. Therefore, if you have a coarse grain sample versus a nanocrystalline sample, the diffusion behavior will be dramatically different. And diffusion can happen much faster in the nanocrystalline material due to the higher volume fraction of grain boundaries. Second, free surfaces in samples can also act as a highway for diffusion. This is why when we do heating experiments inside TEM samples are essentially thin foils. A lot of diffusion can happen on the TEM sample surface instead of inside the material. That's something we need to bear in mind. after establishing the understanding of diffusion in a qualitative way. In the next two videos, we'll look at diffusion in a quantitative way. We will introduce Fick's first law in the next video and Fick's second law in the video after.